So for the do now, it gives us a balanced equation with a delta H value and says calculate the amount of heat that is evolved in kilojoules from the reaction of 25 grams of Na2O2 with water. So we've talked about different ways to calculate delta H. To figure out which way you use, just look at what you're given. The problem doesn't say anything about a calorimeter, right, or things being added together, so it's not a calorimetry problem. We don't see multiple equations with delta H values, so it's not a Hess's law problem. Instead, they give us one amount of something, and they're asking us to go to something else. So I'm going to start by writing my given information down. They give us 25 grams of Na2O2, and they ask us to go to heat. So just like they asked us to go to moles of something or grams of something, instead they're asking us to go to heat. So this is a thermochemical equation. This is just going to be stoic. So I'm going to take my grams, and before I do anything else, what should I convert my grams to? Moles. I'm going to go from grams of Na2O2 to moles of Na2O2. So 2 NAs plus 2 O's. Molar mass of Na2O2 is 77.98 grams for 1 mole. So my given information is now in moles. Now that my given information is in moles, just like I were doing a stoichiometry problem, in stoic, to go to something else, we use the mole ratio. But instead of a mole to mole ratio, I have this balanced equation up here. All of my coefficients represent the moles of reactants or products, but I also have this delta H value. So I'm going to go from moles of Na2O2 to kilojoules. And so to go from moles to kilojoules, I'm just using the molar heat ratio. So for every 2 moles of Na2O2, because there's a 2 in front, it releases 126 kilojoules of heat. So again, if we look at what we did, we took our given information, which was grams, we went to moles. You always want your given information to go to moles. Then we converted from moles to kilojoules. Notice how this is not 1 mole of Na2O2. It's whatever your coefficient is in the balanced equation. So we take 25 times negative 126 divided by the quantity 77.98 times 2, negative 20, 0.2 kilojoules. So if you're given a balanced equation with a delta H value, just one balanced equation, and it asks you to calculate something when it gives you just one given piece of information, more than likely we're going to use the thermochemical equation, and we're just going to stoic from our given to whatever it's asking for. Biggest thing is this is what is different from stoic. So instead of moles to moles, it's moles and kilojoules. And we could go the other way. They could give us heat and ask us to go to grams or to moles. So we just go the other way. We have kilojoules on the bottom, moles on the top. Any questions on the do now? So if you flip to page 10, we're going through example 4 together. All right, so again, in your notes, it's page 10. I'm going to talk a little bit about how solution calorimetry is different from what we've looked at. And then we'll look at how we actually are calculating. So, solution calorimetry. We looked at calorimetry last week where we looked, actually in the specific heat lab, we looked at Q metal plus Q water equals 0, or the idea that the heat that is released by the metal is absorbed by the water. First law of thermodynamics. The only difference between calorimetry that we looked at last week and the solution calorimetry that we're going to look at today, so it's the same process, but instead we actually have a reaction occurring in the calorimeter. So for the metal, we just poured hot metal into water. There's no reaction occurring. Solution calorimetry, we typically have a reaction occurring, and the reaction occurring is either reactants, forming products, or a solid dissolving in water. So it's a little bit different in terms of our thought process. So instead of having Q metal and Q water, we're actually going to be focusing on the heat of the reaction and the heat of the solution. So those are our two labels that we'll have for Q. So when we're thinking about our system and our surroundings, because we always have to think about what are all of the different systems in the calorimeter. The reaction that is occurring is actually the system. So this was in the Do Now last week when we looked at what happens when you dissolve something. So the reaction is the system, the water, the solution that is forming, that's all the surroundings. So when we're thinking about is it exothermic or endothermic, we have to think that the reaction itself is the system. Everything else is the surroundings. So it's a very abstract system. It's just the reaction that's occurring. When we're calculating delta H, so when we're calculating delta H, a lot of times it's going to say calculate the heat of reaction or delta H reaction per mole of something. And so we have to make sure that we're paying attention to the number of moles, or we might have to calculate the number of moles in the reaction in order to actually find delta H. Remember, Q is what we calculate using the first law of thermodynamics, but then to get delta H, we have to divide by moles. So during solution calorimetry, notice the setup is still the same. Q reaction plus Q solution equals 0, but instead of it being, Q combustion plus Q water, it's reaction and solution. Q reaction is typically what we're solving for. So Q reaction is what we solve for. Q solution is what we plug variables into. For Q solution, when we plug values into Q solution, it's still MC delta T. But M is the mass of the entire solution. C is the specific heat of the solution, which is typically the specific heat of water. And then delta T is going to be what delta T usually is. Delta T is usually the same for everything. The biggest thing that people miss is the mass. It's the mass of the total solution. So you're adding your two reactants together, the total mass of the solution. If it gives us a calorimeter constant, then we're going to have Q reaction plus Q solution plus Q cal equals 0. So we just have to pay attention to what our systems are. There are a couple questions like this on mastering, 14 and 24. 24 is an extra credit question. 14 is not. But these are two types of solution calorimetry questions. So if we take a look at example number 4. So for example number 4, it tells us that we have HCl and KOH combined in a calorimeter. So HCl and KOH, they give us the amounts of each, are combined in a calorimeter. So right there, that tells us we have a calorimetry problem. It also, says calorimetry in big letters at the top. But if you didn't have that, it tells us that we're mixing two things in a calorimeter. Temperature of the calorimeter in both solutions goes from 25 degrees to 29.6 degrees Celsius. Assume the specific heat and density of each solution is the same as water. Heat capacity of the calorimeter. All right, so they give us the heat capacity of the calorimeter. That means I have to take into account Q cal. I'm just going to put a star. This is not Q cal, but this is telling me I have to take into account the heat from the calorimeter as well. Calculate the heat of reaction per mole of HCl. I want you to change that in your notes. Yours says per mole of water. Change it to say per mole of HCl. So the very, very last thing calculate the heat of reaction, which is delta H reaction, per mole of HCl. Not water, HCl. Now, they actually tell you that the specific heat of water is 4.184, and they tell you that the density of water is 1 gram per milliliter in the example. I didn't put it up here to save some space. So, I'm going to kind of split this into like 2/3 and 1/3. And the reason is over here I'm going to do any extra work. Over here I'm going to actually do the calorimetry problem. So I'll show you like in my notes. See, I did like part of it over here, part of it over to the side. So in this it says HCl and KLH are combined in a calorimeter. So we actually have a reaction occurring. HCl plus KOH. We have a reaction occurring because we're mixing two things together. So we form KCl plus H2O. So we have an actual reaction occurring in the coffee cups. The HCl and the KOH react to form KCl and H2O. So since there's a reaction occurring, one of our systems is Q reaction. When you mix two things together, you also are forming a new solution. So we're also going to have Q solution. Now, because they gave us the heat capacity of the calorimeter, we also have to take into account QCal. So we have three different focuses in this calorimetry problem. We have the reaction that's occurring, we have the solution that's forming, and we have to take into account the calorimeter. If they would have not given us heat capacity of the calorimeter, we would not have to include QCal. You only have to include QCal when you are given the heat capacity of the calorimeter. Now, the problem says calculate the heat of reaction. Now, I know it says delta H. We'll get there eventually. But if I'm calculating heat of reaction, I'm going to actually solve for Q reaction in this problem. So I'm going to leave Q reaction alone. That's my variable I'm solving for, which means I'll be able to plug something in for every other variable. So if I look down here, Q reaction, I'm leaving that alone. I'm leaving it as Q. That's what I'm solving for. So I'm going to plug in variables for Q solution and QCal. Right. Q is MC delta T. So for Q solution, it's going to be the mass of the solution, specific heat of the solution, times delta T. Q is MC delta T with the exception of QCal. Now I wrote SOLN, that's shorthand for solution. So whenever you see SOLN, that's solution, just like RXN is reaction. We have to make sure we're taking into account the solution here. Then for QCal, that's just CCal times delta T. Remember that the calorimeter, heat absorbed by the calorimeter, if you look at the units, it's just joules per degree Celsius. There's no mass included there. So again, I'm solving for Q reaction. I need to plug in information for every other variable. So this is why over here off to the side, I'm going to show how to calculate these. So to calculate the mass of the solution, they give us some important information in here. So they tell us that the specific heat is the same as water, so that's going to be useful for C. But then they tell us the density of each solution is the same as water. Density lets us go between mass and volume. What's the total volume when the two solutions are mixed together? 100 milliliters. So the total volume when the two are mixed together is 100 milliliters. Now they give us the density so that we can go to grams. Now it tells you in here the density is 1. So for some people, they'll just look and say, okay, 100 grams, or 100 milliliters, 100 grams. Here's how we can actually, this is how we would solve. Because if we have 100 milliliters, water's density is 1 gram per milliliter. So the mass of solution is 100 grams. If this were 60 milliliters and 50 milliliters, that's 110 milliliters, would be 110 grams. You always have to take into account the mass of the entire solution. If it were a solid dissolving in water, you would add the mass of the solid to the mass of the water. Okay, so C, they gave us the specific heat. I just want to calculate delta T over here as well. How do I calculate delta T? What minus what? Which temperature do I subtract from which? Final minus initial. Every single time it's final minus initial. So it goes from 25, that's my initial, to 29.6, that's my final. So 29.6 minus 25. My delta T, 4.6 degrees Celsius. Notice how the temperature of the calorimeter and everything inside. So this is the delta T for everything. So now I have everything. I should be able to plug everything in. So again, I'm leaving Q reaction alone, because that's what I'm solving for. Mass of the solution, we said, is 100 grams. Specific heat of the solution is the same as water. Typically in solution calorimetry, your specific heat is the same as water, because that's the universal solvent. When we dissolve something in water to create a solution, it's dissolved in mostly water. So 4.184 joules per gram degree Celsius. Delta T, 4.6 degrees Celsius. So MC delta T. And then C cal delta T, 125 joules. So joules per degree Celsius times delta T. So the only difference between solution calorimetry and what we've been doing before is that instead of water, it's now Q solution. So 100 times 4.184 times 4.6 is 1924.64 joules plus 125 times 4.6 575 joules, and then it just becomes algebra. Plus 1924.64. So I'm showing every single step so you can see how I'm getting everything. So I added the two like terms together. I could add them together because the units were the same. They're both in joules. So then Q reaction is negative 2,499.64 joules. Now that's Q. Right, that's Q. That's heat for a certain amount. It wants heat of reaction. Heat of reaction is delta H. Delta H is the unit kilojoules per mole. And specifically, this one's per mole of HCl. So over here, I'll go ahead and I'll do moles of HCl. So in order to figure out delta H, I need to divide this by the moles of HCl that were reacted. They give me 50 milliliters, 0.75 molar. So remember that molarity is moles over liters. Molarity is a way for us to go between moles and liters. We use molarity as a conversion many times. So molarity, 0.750 molar is X moles, and then be careful with what's on the bottom. It needs to be in liters. 50 divided by 1,000 is 0.05. I'm going to put a little star here. Remember that it has to be in liters. So if I solve for X, I'm going to multiply over 0.0375 moles of HCl. So 0.0375 moles of HCl. So now I can solve for delta H. And to solve for delta H, I can divide this by 0.0375 moles of HCl. Now delta H is usually in kilojoules. So you could solve this and then just put it into kilojoules, but I'll show you how you can do it here. So for kilojoules, there are 1,000 joules. So I just did it all at once. Some people will be like, can I just convert my joules to kilojoules first? So it would be negative 2.49964. Yeah, you could do that. That's fine. Whatever order you do it is fine, as long as you're getting the same thing. So negative 2499.64 divided by 0.0375 divided by 1,000. Delta H is negative 66.7 kilojoules per mole of HCl. So the difference between what we've been doing and solution calorimetry is the reaction versus the solution. Reaction is always what you're solving for. When we do lab calculations, reaction is what you're going to solve for. And then when you're doing solution, make sure you're taking into account the mass of the entire solution.